We're looking for positive integer equations today. And a common approach is to square the left-hand side and the right-hand side, obtaining this result. And this is an approach, I've seen it done this way. Again, this is a familiar a plus b quantity squared identity. And if you do that, you would end up with this. And you could actually go to work on this equation. But notice you're still left with this radical right here. Okay? And I've seen some people do it this way. I'm going to show you another way, and it's another way for me. I'm sure other people have seen this, but it was new to me. Okay, so again, this is an approach, but we still have to deal with these two radicals, the product of these two radicals, and so I'm trying it another way. And what I did, folks, is I actually just chose to factor out a square root of x. All right, I factored out a square root of x. I got this expression that the algebra is pretty easy to see. Now, an important fact here, the reason why this is equal to 9 times root 7 is 567. And this is some fairly simple arithmetic. 567 is equal to 81 times 7, right? And so one of the properties of radicals is that when you take the square root of a product, it's the product of the square roots. And that's where we get 9 root 7 right here, okay? Now, again, this factorization would motivate the try 7, right? We are looking for natural number solutions. So let's pop 7 in there and see what we get. The next line will show us that. Okay, this is exactly what happens when we substitute 7 here and here, okay? And when you do that, I won't go through all the arithmetic, but you do get y is equal to 448. This is very, very straightforward right here. Again, this calculation, set it equal to 9, and excuse me, my bad. I didn't write something down. What we did, folks, is we yeah, I left that out. Okay, folks. So this original expression was equal to 567. And when we factored it, it's still going to be equal to the factored form. And so what happens here, though, when you divide through by root 7, you get this statement right here. Glad I caught that. Okay, root 7 divides both sides. You end up with this statement, and then simple arithmetic yields y is equal to 448. Notice that we subtracted 1 from 9 to get 8, and this part right here is 8 squared. Okay, this piece right here is 8 squared. All right, and then when you multiply 7 times 8 squared, you get this value. Excuse me, when you solve for y, you get 448. Okay, now so that indicates that 7 and 448 is a solution. The natural numbers x equals 7, x equals 448 is a solution to this equation. And also notice that this is in the form. If you take a look at the form of this that led to this. And this is superfluous, but I'm going to write 1 root 7 plus 8 root 7. Okay, now that's certainly equal to our desired constant on the right-hand side, which is 9 root 7. Okay, in those two solutions, these two guys right here squared are these values up here, okay? So you see that's kind of cool how that works out. Now the very same thing happened, this pattern where we have these integer coefficients summing to 9 like we do right here, that's going to repeat. See right here we have 2 plus 7 also sums to 9. And notice that leads to x equals the square root of 28. Remember, because if x is equal to 28, the square root of 28 is exactly this piece right here, right? Remember, 28 is 4 times 7, right? And again, I won't write down all the arithmetic of that. I'm sure you all see all of that. So again, if x is equal to 28, then the square root of x is this number you see right here. And a similar thing, 7 root 7 and 343 correspond to each other also, okay? So this piece right here is the square root of 343. So you're kind of working backwards, and it's easy to do these computations without having to write too much down, okay? So we found another solution, x equals 28. I won't fill all these in because you guys can read it. It's not that imperative to write every last step down here, but this would be another solution. Okay, and then again, a very similar type of thinking goes all the way down here. 3 and 6 sum up to 9. You end up with the corresponding solution 63,252. And also 4 and 5 sum up to 9, and you end up with the solution x equals 112, y is equal to 175. Now, I do want to make one comment that I probably should have made at the very beginning. We could have just as easily written this as, I'm talking about this idea of symmetry. We could have just as easily written this as root y. We could have factored root y out, still have the 1 plus root x over y. Root x over root y, excuse me. All right, so you see that creates this sort of symmetry. It doesn't make any difference which variable we factor out. We get similar type of processing right here. And so not only is, where did I write it here? Yes, right here. Not only is 28,343 a solution, but 343 and 28 would also be a solution. Okay, and again, some people just kind of brush that off and say, oh, it's symmetry. Well, it's symmetry, but that's the reason why, because the variables are kind of equivalent to each other. I guess that's, I don't know if that's correct language or not. But anyway, this is a solution. So for each ordered pair, you can flip the x's and y's, is what I'm trying to tell you, okay? So there's actually, how many solutions do we have? I guess there's 8 total solutions. I never explicitly wrote this one down, but the solution up here would be 64, 448. And as we've seen, because of the symmetry, that would also, there would be a dual solution, 448, 64, okay? So again, by my count, folks, there were 4 of these original conditions. 1, 2, 3, 4, but each of these 4 conditions that satisfy the initial conditions correspond to 2 solutions, okay? So that would be 8 total solutions. All right, so we have 8 total solutions. Hopefully I've listed them in a way that's marginally intelligible and given you a way to do this without having to square the original expression. All righty, thank you for viewing.